Okay, then let's start the last talk today. The speaker is Professor Anna Caraiani from Imperial College London. The title is A Comparison Theorem for Ordinary P-adic Modular Forms. So please start.
Well, thank you very much for the invitation. I should say it's really a great honor for me to speak at this conference that's dedicated to Professor Saito. When I was a PhD student, I read one of his papers, which is the one where he sort of gives a very conceptual construction of the weight spectral sequence. And that ended up being the key to my solving my PhD thesis. And so I have looked up to Professor Saito for a really long time. Right. And so what I want to talk about today is joint work in progress with Elena Mantovan and James Newton. And what we want to do is give a new proof of an older result that is originally due to Ohta about sort of comparison theorem between sort of that relates different definitions of ordinary p-adic modular forms. And sort of we're interested in this because we're trying to understand how one might generalize to, say, other Shimura varieties. But for now, this is work in progress, and we're really just looking at the modular curve. So I'm going to take, let's see, G to be GL2 over Q. And I'm going to look at some level, which is sufficiently small. And I'm always going to assume that my tame level is fixed. And sometimes I'm going to have hyperspecial level at P, and sometimes maybe I'm going to allow the level at P to increase. Right, so this is the level, assumed sufficiently small. And then I want to look at the modular curve, both sort of the one that's defined moduli theoretically, and its compactification that you obtain by adding cusps. So these are curves over Q, and this xk is smooth and projective. And over yk, I have the universal object, universal family of elliptic curves. I'm going to denote this map by F and the unit section by E. Right, and so I want to look at the automorphic line bundle, which is obtained by taking the pullback of the relative differentials of E over yk, which actually extends to xk. And so modular forms can be defined as sections of various tensor powers of this automorphic line bundle. More specifically, I'm interested, say, in the space of cusp forms. So I can look at H0 of xk, and I want to take the kth tensor power of omega k, and I want to allow zeros at cusps. And this would be a space of cusp forms. Of level k and weight k. But the space of cusp forms, so if you think about it this way, this is something that is defined using the coherent cohomology of the modular curve. But of course, this also contributes to the Betty or the et al. Cohomology. Via the Eichler-Shimura isomorphism. Or xk, or here I can put yk via the Eichler-Shimura isomorphism. So the Eichler-Shimura isomorphism is going to sort of compare Betty cohomology with Theorem, I guess, Theorem cohomology, and where you see this contribution from these global sections over the automorphic line bundles. If you think about et al. Cohomology, maybe the more natural way of comparing these is sort of via, say, the Hodge-Tate decomposition. So let me say Falting's is Hodge-Tate decomposition. So here I'm going to take some k, and I'm going to define mu k to be the kth symmetric power of R1 F lower star of ZP. So F is the map from the universal elliptic curve to YK. Or yeah, I mean, this also extends to XK if you want. So this is, but I just need to think of it as a local system on YK. And here I'm going to assume that K is at least 0. And I want to take a perfectoid field. So take an algebraic closure of QP and take the p-adic completion of that. So then Faltings's Hodge-Tate decomposition is going to relate the et al. Cohomology of YK with sort of two spaces of coherent cohomology. So let's see, H1 et al. And I'm going to look at cohomology with compact support because I'm interested in understanding cusp forms of YK. Let's say base changed to this perfectoid field C. And here I extend the scalars to C. So this admits a decomposition, first say a short exact sequence, and then this short exact sequence has a canonical splitting. So here I would have H0 XK, again, base change to C, differentials on XK, tensor omega K to 0, and coming in, we have higher coherent cohomology, H1, again, XK, omega minus K, and with zeros at cusps. Okay, so there is such a decomposition which admits a canonical
Excuse me,
split.
for your et al. Cohomology, you want to have some question, right?
Sorry?
You put ZP for et al. You put ZP for et al. Cohomology, but you want to have weight K.
Yes, you're right. Sorry. You're right. Yes, thank you very much. Yes, of course. I want to put the local system that I constructed. Right. And this admits a canonical GQP equivariant splitting. And this H0 space over here is the space of cusp forms of weight K plus 2. And this space here is dual to it under coherent duality. Anyway, but this is sort of an old result that kind of explains how you might compare these different cohomologies in the case of the modular curve. And the goal for the talk is to obtain a version of this decomposition for, well, we want to work in families. So basically p-adic families of modular forms, and a nice p-adic family that whose construction goes back to Hida is, in fact, the first p-adic family is ordinary. The family of ordinary p-adic modular forms. And this is something that we want to do even integrally. So without inverting P, say with say coefficients in ZP or right. And the reason why you might care to do this integrally is because, for instance, in higher dimensions, you can see torsion phenomena. But right, and as I said, this is something that has already been done by Ohta, but our goal is sort of to give a new proof that exploits some recent developments, both in the theory of, say, Shimura varieties, of which the modular curve is an example, and also in the theory of p-adic automorphic forms, where there is these new constructions of higher Hida theory due to Pilloni and Boxer Pilloni that construct families by p-adically interpolating coherent cohomology in degree more than 1. Okay, so this is the goal. And so the first thing is I want to talk about ordinary p-adic modular forms in the Betty or et al. Setting. And here, I guess there are two approaches one could take. And I have my preferred approach, which is to use ordinary completed cohomology. One can also study these things using modular symbols. But I'm going to use the approach using completed cohomology, which goes back to Hida and then was developed more by Emerton. So let me define, I mean, one can do this in a sort of fancy way and one can do it in a very concrete way. So maybe sort of the fancy, more conceptual way is to look at completed cohomology, which would be a direct limit over the level at P, going over compact open subgroups of GL2ZP of the cohomology. And here, again, I want to look at compact support of YK of C. And here K is supposed to be, so my fixed time level, and then this varying KP, and with coefficients in Z mod P to the N. And one can even form a sort of p-adic version of this, where you take an inverse limit of the previous things over N. And I don't want to sort of go into details of sort of how precisely to construct these, but let me just say that these complexes have cohomology that has nice finiteness properties. So the cohomology is, for instance, p-adically admissible. It's a p-adically admissible representation of GL2QP. And because of these nice finiteness properties, for instance, Mittag-Leffler is satisfied, and so it doesn't matter whether I take lim or R lim or anything like this. So this object is called completed cohomology, and this is what was introduced by Emerton, I guess more than a decade ago now. And I guess it's quite a complicated object. So for instance, since we're doing the modular curve, it sees the p-adic local Langlands correspondence for GL2QP. So it is quite a complicated object. It's something that makes sense whenever you work with, say, any Shimura variety or even a locally symmetric space that doesn't have the structure of a Shimura variety. So this gives a very general way of defining families of p-adic automorphic forms using the Betty cohomology of locally symmetric spaces. And so that's something that's very appealing about it. But sort of this object is too complicated for my purposes. And so I want to cut it down, and by cutting it down, so by that I mean I want to sort of apply Emerton's functor of ordinary parts to it. And I guess I'm working with derived things, so let's say derived ordinary parts. But then I'll also give you a very concrete way to think about this. So this consists of some steps. So first I want to look at, say, the standard upper triangular Borel inside my group, which is a semi-direct product of the diagonal torus and the unipotent part. And just to introduce some notation, I'm going to say B0 is B of ZP, T0 is T of ZP, which is just two copies of ZP cross. And N0 is N of ZP, which is just isomorphic to ZP. Right. And so to apply Emerton's functor of ordinary parts, the first thing is that you want to apply continuous cohomology, so continuous group cohomology of N0 to each of these terms. Then you want to invert the UP operator. So the UP operator is going to be a Hecke operator that exists at this level. So for instance, it would go from R gamma. Let me skip the continuous. So whenever I do group cohomology of N0, I mean continuous group cohomology. So this to say U and 0 U inverse, where U is the matrix P001. There's a U up or a pullback map. Now, this is going to be something that's smaller, contained inside the ZP points of the unipotent, and there's a trace map back to the original object, and this whole thing gives you the UP operator. And you want to just look at the part where the UP operator acts invertibly. It turns out to be sort of equivalent to, say, take something called locally finite vectors under the UP action. Or it turns out that because of the finiteness properties that this cohomology the cohomology groups of these complexes satisfy, it's actually just a direct summand of the original object. And finally, you want to take an inverse limit with respect to n. And it's important to first invert the UP operator and then take the inverse limit. Otherwise, you get something bigger. Okay, so concretely, the object that you get I'm going to call it H1 tilde with compact support ordinary. So this is what is going to be ordinary completed cohomology. And this is going to be an inverse limit with respect to n, direct limit with respect to m, H1 with compact support of our modular curve with coefficients in Z mod p to the n. Here I take ordinary parts and then I take the inverse limit with respect to n. Right, so this is what ordinary completed cohomology is supposed to be. And one thing that's nice is, so you can define it in the derived category, but it turns out that when you apply ordinary parts, only 1 degree of cohomology survives. And so it's just, it's as simple as you would want it to be. And of course, if you want to work with this kind of thing more generally, then you would have more degrees of cohomology to worry about. But for the modular curve, this is very nice. Right, and somehow, so this is basically, this is a p-adically admissible representation of T naught. So it has nice finiteness properties, and it's a representation of T naught, which was this ZP cross times ZP cross. It turns out that and I should say, I've said this, but let me just write it down. So this is something that was originally introduced by Hida, and then one can also reinterpret it using this machinery of Emerton. So like the completed cohomology at full infinite level, and then applying this functor of derived ordinary parts. Sorry, and here I want to take y, of course, I have to take a limit over the level at p. So y, k1, p to the m. Right, so the whole point is that the level at p increases. K1, p to the m is, so whatever my original level was, I want to keep imposing congruences where these matrices are unipotent modulo p to the m. So that in the limit, you can think of this as being the cohomology of the modular curve at this level n0, at this unipotent level. Right. So let's see. And for later purposes, it will be good to think of this sort of on the dual side. So let me say that I take lambda to be the Iwasawa algebra of the torus. So this is going to be sort of like a weight space. So this is going to, sort of keep track of the different weights of the modular forms that we're looking at. Because when we want to do things in a p-adic family, we also want the weight and the level at p to vary. So lambda will be the Iwasawa algebra. And then I want to say that this object, this ordinary completed cohomology, is sort of dual to a finite projective lambda module. So it's as nice as you could hope for. And this is something that is slightly non-trivial in the sense that it turns out, so to actually get something that is projective over the Iwasawa algebra, you need to know that you have cohomology in 1 degree, and not just at this level, say n0 given by the unipotent, but really at level b0, where b is the Borel again. So somehow this turns out to work when you apply ordinary parts in the case of the modular curve, but it's sort of something quite special. And it's related to the fact that you have cohomology in 1 degree at this low level. And so what do I mean by dual? I want to sort of really have like I have a particular functor in mind that I want to apply to ordinary completed cohomology. So let's say define a functor mn for each n, say z greater than 1, which goes from, let's see, smooth admissible representations of T naught with z mod p to the n z coefficients, to finitely generated modules over the Iwasawa algebra with z mod p to the n coefficients. And this functor is going to take, say, an object in here to basically, I want Pontryagin duality, but I want a double dual. So I also want to take a dual with respect to this Iwasawa algebra. So Hn Pontryagin dual, and then I take the dual of this with respect to the Iwasawa algebra. And this is something that's slightly complicated, but it turns out this kind of duality is also what happens when you try to understand Poincare duality for ordinary completed cohomology and say try to relate it to ordinary completed homology. And so I'm going to define M1C tilde to be the inverse limit with respect to n of Mn ordinary completed cohomology with compact support, but I reduce it mod p to the n. Then it's an object in this category. I can apply this functor, and then I take the inverse limit. And this is the one that will be a finite projective lambda module. And it's closely related to some kind of ordinary completed homology, except that one needs to be careful about sort of how one forms the projective system when one talks about completed homology. Right, but it's roughly the same information that you see in the space of, yeah, like in the original ordinary completed cohomology is just some duality that will turn out to be convenient for comparing to the p-adic families that one obtains on the coherent side. All right, and I think that now I want to move to talking about the coherent side, unless there are some questions about the Betty or the et al. Side. All right, so I want to now talk about p-adic modular forms or ordinary p-adic modular forms in the coherent setting. And this is, so there will be two spaces of ordinary p-adic modular forms that we care about that are dual. And the original construction is due to Hida, one of them. And then the other one you can obtain as its dual, but more naturally, it's constructed in a 2020 paper of Boxer and Pilloni. So higher Hida and Coleman theories for the modular curve. So now I want to really say assume, right, that my level is of this form with Kp equal to just GL2CP. And then I have a nice integral model of the modular curve. And let's say, yeah, sort of X over ZP is the integral model. And I'm going to suppress the level. And I want to look at the ordinary locus, which is open and dense inside of it. And in fact, I want to view it as a formal scheme. So I want to take the formal completion of the integral model along the ordinary locus. And this is an affine formal scheme over SPFCP. And it's affine because it's defined by the vanishing of the Hasse invariant. So I have my universal elliptic curve, or maybe it's an extension to a semi-abelian scheme. So I can talk about a p-divisible group. And let me not worry about exactly what happens at the cusps. Things will work fine at the cusps if you are careful about how you extend them. So this over the special fiber, so let's say X ord is just over spec FP. Right, this is the universal p-divisible group. Because you're restricted to the ordinary locus, it has a slope filtration. Which is just consisting of a multiplicative piece and an étale piece. So G naught, G étale. Right, and the Igusa tower is a pro-finite étale cover of the ordinary locus that trivializes the graded pieces of the slope filtration. So G naught and G at. And one advantage of looking at the Igusa tower is that, in fact, it it lives over. You can even make sense of it as a p-adic formal scheme, because since it's a pro-finite étale cover, it will lift uniquely. So it's a T0 torsor over the ordinary locus as a formal scheme. And one thing that happens is that it gives a canonical trivialization of the automorphic line bundle omega. So over here, we have omega is isomorphic to there's a canonical trivialization where you can identify it with the structure sheaf. And that's because you're trivializing this, these graded pieces of the slope filtration. And so, when you think about modular forms of weight K, so you want them to be sections of the K tensor power of omega. And so if you trivialize omega, that's a really good first step towards p-adically interpolating things with varying weight. So that's why it's very natural to consider this Igusa tower. And there is a Hecke correspondence over the Igusa tower. Which I'm going to write for sort of just mod p at first. And this is just pulled back from a correspondence that already exists on the ordinary locus. So mod p, the bar will signify mod p. You have, on one hand, the relative Frobenius on the Igusa tower, and I'm going to call this P1. And on the other hand, this is just an isomorphism, and I'm going to call this P2. So this gives rise to a correspondence, P2 upper star, the structure sheaf, P1 upper shriek. So a cohomological correspondence over the Igusa tower, which, because this P2 is just an isomorphism, can be identified with the trace of Frobenius. And something nice that happens is that F has a canonical lift to characteristic 0. which is given by the sort of theory of the canonical subgroup. So the moduli theoretically, this is just, so let's say the canonical lift is called F tilde, and moduli theoretically, F tilde is given by taking a quotient by the canonical subgroup. So there is a canonical lift of the multiplicative piece of the slope filtration. Right, and so once you have this, you're in a good position to talk about Hida theory, by which I mean the theory in coherent homology in degree 0. So I'm going to call this H0. So global sections over the Igusa tower of differentials with logarithmic poles along the cusps, and tensor some ideal. And then I want to take the part where, let's see. So I'm going to take UP naive to be this correspondence here. Right, and J is just the ideal of the cusps. That's because I want to talk about cusp forms throughout. So this would be the space of ordinary p-adic cusp forms as Hida defines it. And there's you can, using the Kodera-Spencer isomorphism, you can identify this with just global sections of the Igusa tower of this, just the ideal of the cusps. Taking ordinary parts with respect to a renormalized UP operator. It turns out that the naive UP operator, if you just think about it acting as a correspondence on homological correspondence for the structure sheaf on the Igusa tower, is divisible by P. So you have to renormalize it. Right. So that's one space that one can consider. So this one, or sort of the ordinary part of just the global sections over the Igusa tower. What Boxer and Pilloni work with, for instance, in order to construct families, so finite projective modules over the Iwasawa algebras, they work with something that's dual. And so on the dual side, you can look at the universal character of the ZP points of the torus, so valued in the Iwasawa algebra. And you can form quasi-coherent sheaf on the ordinary locus by sort of descending along this universal character. So you can define something. So you take your original sheaf, which could be the structure sheaf or the one that's given by the ideal of the cusps, take completed tensor product with the Iwasawa algebra. You project this, pi is the T0 torsor. So you project along the T0 torsor to the ordinary locus, and then you take invariance under T0, under the diagonal action of T0. And so you get a quasi-coherent sheaf that corresponds to this universal character. And so, for instance, if I want to specialize in weight k, then I would get the kth power of omega k, well, tensor with the ideal of the cusps. So you can define as a finite projective lambda module, you can look at H0 XORed of this omega kappa, so the universal sheaf on the ordinary locus, and then take ordinary parts with respect to the UP operator. And this turns out to be exactly dual to H0 that we considered initially. So in terms of this functor that I defined earlier, you can identify this with the inverse limit with respect to n of mn H0 modulo p to the n. So it's just this same functor applied. And this is something that ends up being a finite projective lambda module. This is something, say, proved originally by Hida. And the proof relies on the fact that the ordinary locus is affine, which means that it's you're only going to have a coherent cohomology in degree 0. And also, sort of the finiteness comes, or at least I think it's pretty subtle if you don't know something extra. So to get that it's really a finite projective lambda module, you need to know that some of these ordinary p-adic modular forms are in fact classical. And so you can obtain them as sections of an automorphic line bundle over the entire modular curve, which is a projective curve. So you also need to use classicality, which happens in weight at least 3. And so, for instance, you can reduce modulo the maximal ideal of the Iwasawa algebra. And so to get finiteness, sort of it's enough to understand classicality in kind of, a set of representatives for the mod P congruence classes of the possible weights. So, weight greater than or equal to 3 is enough. Right. So it turns out you can do the same thing with higher coherent homology if you consider homology with compact support. So this is going to be higher Hida theory. So you can look at H1 with compact support, which I can define as just H1 over the Gusa tower of this ideal or sheaf J. And then sort of one subtle thing is that you don't take ordinary parts with respect to the same UP operator or UP naive, but you take ordinary parts with respect to this lift of Frobenius. And that's because you have this diagram over here. And it turns out that really sort of the natural way to think about this is to really think about the ordinary locus at Iwahori level that has 2 components. And one of the components is the one that gives rise to Hida theory, so cohomology, coherent cohomology in degree 0. And for that, you have this diagram. And the other component of the ordinary locus is the one that gives rise to higher Hida theory, so H1 with compact support. And there, the correspondence looks reversed. So I have to take sort of P1 to be the isomorphism and P2 to be the canonical lift of Frobenius. And then if you write down that cohomological correspondence, it just amounts to pullback under this F tilde star. Right. And so this is the thing that is defined in this recent paper of Boxer and Pilloni. And then on the dual side, you can take M1C, which is H1 with compact support of the ordinary locus with coefficients in this universal sheaf. And just one comment is that cohomology with compact support here, so it's cohomology with compact support of coherent sheaves, and one can use the old definition due to Hartshorne. And that a priori, some of the things that you do depend on the choice of compactification, or at least, Hartshorne proves that it's independent, but one needs to be careful. Say, when you take ordinary parts, you need to go to a compactification. And so there is some care that one needs. But let me just say that these are again related by this functor Mn that I defined. So this again can be identified with inverse limit with respect to n of this functor. Right, and again, this M1C is also a finite projective module over the Iwasawa algebra. And again, affineness and coherent duality will tell you that cohomology is in 1 degree. And for finiteness, you need some classicality. And the classicality is going to be in weight sufficiently small. So affineness plus classicality and weight less than or equal to -1. So again, so that you can really identify them with sections of some automorphic line bundle over the projective, or not sections, but coherent cohomology of some automorphic line bundle over the projective compactified modular curve. Right, so at this point, I think I've sort of defined all the objects that go into this comparison result. So let me state the theorem. And this is joint work with Elena Mantovan and James Newton. And it's still in progress in the sense that, well, we're writing the paper. And because of all the inverse limits and the sort of taking ordinary parts and things like this, it's a bit it's been a bit finicky. And so let me just say, yeah, work in progress. So I want to set lambda OC to be the completed tensor product of the Iwasawa algebra with OC. And then I want to say there is a Hecke equivariant short exact sequence of finite projective lambda OC modules So here I have coherent cohomology in degree 1 and with compact support. So this is higher Hida theory. In the middle, I have essentially ordinary completed cohomology, except I apply this functor to turn it into a finite projective lambda OC module. And over here, I have coherent cohomology in degree 0. Let me clarify that this is an M. And this is what one generally refers to as Hida theory. And here, ordinary completed cohomology. Right, and let me say that I have, so 1 and 2, these are the two maps. And I want to say that the first one, I want to say what happens to the lambda action. So where 1 is equivariant with respect to the map that will send T to T1 squared times the universal character, and 2 is equivariant with respect to conjugation by the longest file group element. Right. So this is the statement. And, as I said, this isn't new. So there are already this is proved by Ohta, and there's also a result of case. So you can think of this as sort of a Hodge-Tate decomposition, and then case even studies the Theorem version of the decomposition. And there are also results after inverting P. So let me just write these down. One is, so Ohta and case already sort of proved this with a different method. And 2 is that after inverting P, one can even do the finite slope case. So the first map, so the one that I called, the first map, which goes from ordinary completed cohomology to Hida theory, after inverting P, this would correspond to a result of Andreatta, Jovita, Stevens, and also independently Hoyetsky, Hansen, Johansson. And the second one is a more recent result, I think, maybe early this year, of Juan Esteban Rodriguez Camargo. So 2 is the map from higher Hida theory, or if you invert P, really higher Coleman theory, to he does, I guess, modular symbols, which is sort of equivalent to what you would see from completed cohomology. Right. And so, but the point of what we're doing is that you sort of very naturally see why higher Hida theory shows up with our method of proof. Where I say in Ohta's original result, it's just a dual of Hida theory. And it's sort of really, once you do this, it at least points towards like what might be a general result. At least like it sort of gives you a statement of what to expect. So the idea of proof is as follows. Consists of 4 steps, let's say. So the first step is you want to apply Scholze's primitive comparison theorem to the middle term. So you view your modular curve as an adic space, and you apply the primitive comparison theorem in that setting. So this H1 with compact support ordinary, CP, completed tensor product with OC becomes almost isomorphic to H1, I guess I want to write here quasi-pro et al. Of X and 0, I hat plus ord, where I hat plus inside O hat plus consists of sections vanishing at the cusps. And this X and 0 is a diamond. So it's the inverse limit over all compact open subgroups inside G of ZP that contain N0 of X KP, base change to this perfectoid field C and viewed as an adic space. And so the inverse limit of these adic spaces is at least a diamond. Right, so at least, I don't know, once you apply the primitive comparison theorem, you're at a point where you're sort of slightly closer to coherent cohomology, except that you have this sheaf I hat plus, and you're on the quasi-pro et al. Site of a diamond. Okay, so first step. Second step is you use the Hodge-Tate period map. For the compactified modular curve. So this is going to give, say, I can look at it, say, like this, where I really don't care about what kind of object this is, except a topological space. Right, so the Hodge-Tate period map, say if you want it to be nicer, you have to go to full infinite level, and then it lands into the period domain, which is, in the case of the modular curve, P1. Right, and then the point is that you can use the Bruhat decomposition on the Hodge-Tate period domain. So P1 can be written as a union of, so first I can take the open ball where one of the variables on P1 is less than or equal to 1, and I can take its closure. And this joint union, the Stein ball, where the other one is, this is Z less than or equal to 1, Z less than, Z greater than 1. But let's say, yeah, this is the first variable. Okay, and so this is a decomposition into a closed and an open. And I can also take the preimage of this under pi Hodge-Tate. And because it's the Bruhat decomposition, so it comes from this decomposition into orbits for the Borel, it turns out that the decomposition is stable under the action of N0, so it descends to this unipotent level N0. And so I can write it as U0 bar V infinity. So let's say this is xn0 decomposes as this closed and this V infinity. And in terms of the Weil group elements, this first one corresponds to the longest Weil group element. This one corresponds to the identity. So if you're, say, familiar with this, maybe I should say that. So the identity would really correspond to the, say, the canonical point or the canonical locus on the Hodge-Tate period domain, whereas the longest Weil group element corresponds to the anti-canonical locus on the Hodge-Tate period domain. So, you know, at this intermediate level, N0, you essentially are keeping track of a line inside the P infinity torsion, and that line is either the canonical subgroup, and that's the point infinity, that's the canonical point, which is indexed by the element 1, or it's anti-canonical, so it's as far as possible from the canonical one, and then it gives you the anti-canonical locus, which is indexed by this longest Weil group element. And so let me just say that the short exact sequence in the theorem really just comes from the exact sequence for cohomology with support in a closed subset. So this is going to be H1 with support in this closed subset of xn0, coefficients in I hat plus. I'm not keeping track of the site, but for now we have to work with this quasi-Pro-Étale site. Xn0, I hat plus, and then this goes to H1, V infinity, I hat plus. So over here, I have a neighborhood of the canonical locus. And over here, I have cohomology with support in a neighborhood, or yeah, like essentially the closure of the anti-canonical locus. And so the maps that I had defined before, this was map 1, and this is map 2. And of course, I don't know that at this stage, I don't know that this is a short exact sequence. So this goes on, and this possibly goes on as well. Right, but this is where the maps come from. The third step is that you can massage these into looking like the right terms after you apply ordinary parts. So let me just say nice things happen when you take ordinary parts. So on both sides, it turns out that, so the UP operator either say shrinks or extends your support, depending on whether you're looking near the longest Weil group element or whether you're looking near the identity on the Hodge-Tate period domain. But because you're inverting the UP operator, this gives you an isomorphism. And so you can rewrite, say, H1 U naught bar x and 0 I hat plus as H1 pi Hodge-Tate inverse. So you can just look at the fiber at the point 0. And here I can put any open neighborhood. So it's cohomology with support in a closed, so it doesn't really depend on the neighborhood. I can put, say, pi Hodge-Tate inverse of epsilon I hat plus ord. And that's because, so you can really shrink the support because you're taking ordinary parts. So I'm taking ordinary parts here as well. And now it turns out that sort of pi Hodge-Tate inverse epsilon, so this sort of at level n0 is already perfectoid. This is sort of contained within Scholze's proof that say the modular curve with infinite level NP is perfectoid. And so you can replace the quasi-pro-étale site. It turns out you can just replace it with the analytic site. So that simplifies a lot, right? That there's no more sort of, you're already can think about just the cohomology of a sheaf I plus on this analytic site. And another thing is that it turns out when you take ordinary parts, it really becomes, the UP operator simplifies and it really becomes ordinary parts with respect to this F tilde. And so then you can really compare with H1 with compact support of this, say, Igusa tower with coefficients in something like this. It just amounts to some slightly delicate comparison between cohomology with compact support of a formal scheme and cohomology with support in the adic generic fiber, or like, say, if you want cohomology with compact support of the associated dagger space. But at the very least, you can define a map between the two objects. And on the other side, H1 of V infinity I hat plus ordinary is just because the support shrinks, you can identify it with H1 pro et al. Of, again, the Igusa variety. And here I should put OC. The Igusa variety base change to OC, take adic generic fiber, and then coefficients in I hat plus, and then taking ordinary parts here. And it turns out that this can be shown to be isomorphic. Maybe this part can be shown to be isomorphic to H0 of the formal scheme with coefficients in this and with the renormalized UP operator. And what goes into this isomorphism, on one hand, it's sort of kind of comparing the pro et al. Site on the adic generic fiber. Like if you push this to the et al. Site of the formal scheme, you obtain differentials. This is a result due to Bhatt, Morrow, Scholze. So it's contained within their first paper on integral p-adic Hodge theory, except I guess you need to handle a boundary divisor and you need to work with, say, the log. You need to work with some kind of logarithmic structures. And my understanding is that it's at least forthcoming work of Hansheng Diao and Zijian Yao that would work in that setting. But there may be other results as well. So you need something sort of to relate going from this kind of sheaf, say O hat plus, to differentials. But in order to incorporate the fact that you have a boundary divisor, there's some extra result that one needs. And of course, when Bhatt, Morrow, and Scholze do this, they obtain some junk torsion. But there's also a computation in certate coordinates that you can do So everything is extremely explicit if you work in Caraiani coordinates, and you can see that taking ordinary parts kills this junk torsion. There's some zeta p minus 1, where zeta p is a pth root of unity. And then I'm out of time, but I am at the last step. So let me just write down what the last step is. So this allows you to sort of write down a sequence. So it allows you to write down the maps, but then to actually show that you have a short exact sequence, and it's really a short exact sequence of lambda OC modules, and there's no almost in there. This you can do by using classicality. So these classicality results in weight greater than or equal to 3 or less than or equal to -1. And the fact that you're always working with finite projective modules, so classicality and projectivity over lambda OC, these prove exactness of the sequence and also allow you to remove the almost ambiguity. Right. So yeah, so I'll stop here. Thank you very much for your attention.
Okay, thank you very much. Okay, any questions or comments?
So thank you very much. So you have this short regular sequence. So can you say something on the extension?
Something about what? Sorry, I couldn't hear the
on
word.
The extension. On the extension.
The extension defined by this.
The extension?
Yeah.
This should split. I mean, Ohta proves that it splits, but so we know that it splits because Ohta proves it. However, we would like to find a different reason why it splits. And we haven't done this yet, but it's something that we want to think about. Yeah, no, that's a great question. Thank you.
So you expect something on this extension?
Yeah, I expect that it should be split. I guess maybe his result has some small assumptions, but the way that he proves it is, I think, by looking at the Galois representation. And so he's considering the Galois action as well. And using that, he shows that it has to split canonically. There is some work of Sean Howe that constructs a map in a different direction. So there might be some hope, but he's working after inverting P. So there might be some hope of just kind of geometrically constructing some splitting.
Thank you.
I have small comment maybe related to the splitting of this. Isn't it related also to the work of Hida, who, when he constructed the Hodge filtration over a family, he proved it's just localized in the generic point of the special fiber over the modular curve in the over the base. That in the ordinary case, he has also a Hodge-Tate decomposition, which is a splitting. So I wonder if it's the splitting in some sense is coming from the ordinarity. So, and he explained it in that case in his first work, but this was a very old work.
So who is this? I couldn't hear the name.
Hida.
Hida. Okay.
Yeah.
Okay, I will look into this. I mean, yeah, the splitting is very interesting to us because, and we don't want to appeal to the Galois representation, because when you work with a different Shumurov, right, you're not going to have, like, it's not going to be so easy to just use that. So thank you for the comment.
Any other questions or comments? So what's the expected statement in the higher dimensional case?
Well, in the higher dimensional case, I would expect that. Okay, so somehow if you look at the Hodge-Tate period domain, you would expect that there should be one contribution from each Weil group element, where you look at sort of the Bruhat decomposition. So on one hand, you have your group modulo the parabolic that comes from the Hodge character. And on the other hand, you want to look at orbits for the Borel. And so this is going to be a double coset space that is controlled by a quotient of the Weil group. And you would expect that every, at least say if you have the Siegel case or a group that is split over QP, you would expect that each Weil group element should contribute such a theory. And then there's some work in progress that I saw a talk by Pilloni recently, where they are constructing one version of Hida theory for each sort of Kottwitz-Rappaport stratum at Iwahori level. And these are in natural bijection with these Weil group elements. So you would expect that, yes, like ordinary completed cohomology can be decomposed in terms of these theories. But then you run into issues that say cohomology is no longer concentrated in 1 degree. And so you really have to work with complexes and yeah, it becomes more subtle. There's also work of Giada Grossi, who constructs higher Hida theory for Hilbert modular varieties where P splits completely. And my feeling is that at least in that case, one should be able to obtain generalization of this statement. But even there are some things that are still to be worked out. For instance, the integral p-adic Hodge theory gets more subtle because you end up with kind of spaces that are sort of partially perfectoid and partially look like smooth formal schemes. So I guess yeah, okay. Super perfectoid.
Thank you very much. Any other question or comments? Okay, then let's thank speaker again.
Thank you.
Okay, any announcement?
So we have this gather town for discussions and things like this. So I'll keep it open for about an hour. So if you'd like to